So let's talk about how do we represent a graph. So a graph can be represented in 4 ways. The 4 ways which I know of. There can be more ways. First is adjacency matrix, adjacency list, a generic graph which say we want to make it entirely object oriented, and we want to put our other two representations on steroids and create something entirely different, encapsulated and whatnot. The next is adjacency set or disjoint sets. This is another way to represent graphs, and you would find these graphs and you would find these concepts in when you would have a bunch of graphs who have a cyclic nature, and then there is another bunch which has again a cycle. So you bunch them into a single graph and use disjoint sets there and use union on that. So this is out of syllabus for now, all right? Because I haven't prepared it. So we'll just be talking about these three representations. Adjacency matrix. Adjacency matrix looks pretty easy, and believe me, it is easy. So what we actually do here is we get a list of vertices, and we just map those list of vertices to our rows and columns. And if there is a connection between between two vertices, what we do is we mark them as true, else they remain false. So here 1 represents a true and 0 represents a false. Okay, so like you can see that none of the vertices are pointing themselves, so this particular diagonal would always be 0 because it is the identity matrix thing, where an identity matrix we have all the ones, so identity diagonal, let's call it. Now you know that A is connected to B, A is connected to C, yes, A is connected to, no, not connected to D. B is connected to A, yeah, for sure. B is not connected to B. B is connected to C, yeah. B is connected to D, yeah. So, and similarly, we just keep on filling up this matrix. All right. Now let's move forward. All right. Now this is the code for adjacency matrix. It's pretty simple. It's pretty easy. Now, if you notice, I'll show you in a second. Let's first talk about how we create an adjacency matrix graph. How can we create it? So we are using an array list here. Not array list, sorry. An array here. I always confuse array lists and array. Okay, so we use arrays here. And since we're using arrays, we have to define this bit size at the inception. When it's at the inception, means when we are initializing it. So while initializing, we have to provide a vertex count. And we create our adjacent matrix. That's it. That's all we do. Now we would need to add edges. So we would add edges, between our across our vertices. So here, what we say is that we are taking vertex 1 and vertex 2, and whatever vertices are there, we just mark them as true. And for removal, we just mark them as false. And if we want to find out if there is an edge or not, we just check those vertices if there is an edge or not. Now, if you notice that there is this unusual method here is out of bounds. So what it usually do is, if you notice that this is now being used in all three methods, because I noticed that this particular condition has to be used in all these three methods, and this doesn't look really good to me. And repeating it in all three methods was looking a bit ugly. So why not move it out of these methods and use a common method and refer. So how does it work? I mean, why did we do it? just because it's again a base case which we should always consider. And if our base case is being used by multiple methods in our problem in our data structure, we should make sure that we are taking it out and we are reusing that particular logic in all our methods. The reason is if the logic is same in all the methods, and let's say down the line, if you change anything in your data structure, which results in changing this particular logic, you just have to change it at one place. You do not have to change it at one places, right? So it is always a good practice, even while you are doing, even while you're doing problem solving. Your bugs would be minimal. I know it might sound like a bit more code, but it's much easier when you get bugs, and which you get a lot, right? We do problem solving and we always get bugs. If you do problem solving without getting bugs, hats off to you. I can't do that. None of my programs run on the first time. So let's talk about this time and space complexity. So we know that the number of vertices here is v. So the time complexity here is of the order of v square, and the space complexity is also v square. Why is the time complexity v square? Because here, if you notice, we are initializing our matrix. And while initializing our matrix, it has to fill all the elements in that matrix, and that is essentially an n square operation. All right. Now, one thing I forgot to mention here is that my vertices here, which I'm taking, correspond to the indices, right? But then this data structure can change. I have just kept it. I've kept it like this just for the simplicity of graphs, because it could get a bit ugly if we start using objects here. You can certainly do that, but just for the sake of simplicity and comprehension, let's just assume that our vertices are the indices, right, of our matrix. Now, when we should use these dense graphs? Well, we should always use this dense graph when the number of edges is proportional to the vertices, or we can say when our graphs are dense. What does that mean? What does that mean? So it means that if you notice that every node or every vertex here is connected to the other vertex, right? So if that happens, it's good to use an adjacency matrix. So other than that, let's say if you do not have these connections, then most of our matrix would be empty, and it doesn't make sense to use all that space just for a sparsely connected graph.
All right, folks, that's it for today. And next time we'll discuss about adjacency list.